It's like my situation right now. We're not together, but that's why I do.
It can't be derived.
Oh, challenge. I was on
No. It's not differentiable.
All right, look out, please. Here we go. No worries. Okay, somebody can please. Number one. I'm not sure. Good. Somebody number two. Let's go. Bailey, sorry.
Bird clock. Or jump.
Number three. Let's go. Finley.
Zero or horizontal.
Good guess. We like it, but yeah, that was the correct word. No worries. Ethan.
Corner, vertical tangent.
There we go.
No, right? No. Well, no, it's mine.
Now, hey, the order isn't really important. So you could have said, instead of vertical, you could have had these two. You could have had vertical asymptote here and vertical tangent here. Then full jump or corner could have been in any of the single flanks. It wouldn't matter. Okay. Question? Number four. Let's go here. Perfect. Number five.
Sorry.
David.
So just for F, it's increase, decrease, concave up, concave down, positive, negative, increase, decrease, positive, negative, below.
My bad. Sorry.
Below that.
Nice job, David. Perfect. Number six. Let's go, Rachel.
6.3.
So I'm trying to find the tangent slope of F at x equal 1. So I'm trying to find this slope right there. The graph of F prime, the y coordinate on F prime at x equal 1. So because F prime of 1 is equal to 3, yes, this tangent slope of F at 1 is 3 as well. Question. Perfect. Number 7. Let's go here, Ethan. So similar idea. F double prime of 0 is 20. Which means that the tangent slope of F prime at x equals 0 is also 20. Question. Number 8. Let's go pair. Well done. So right here, the value of F prime and the value of F double prime are the same, which means because F prime of, thank you, Holly. So because F prime of 0.4 has a value equal to 5, that means the tangent slope of F is 5. And then same idea, because F double prime of 0.4 is equal to 5. We know that the tangent slope of f prime is 5 at that same x coordinates. Questions? Cool. Next thing. So let me toss this out. I'm going to give you a sheet protector for this. The sheet protector is indicative of how important what's on this sheet is to understand and never forget the rest of the year.
I get a medium and then I cut it.
The one here.
Where's writing?
Yeah, she looks very much like me. It's like brother.
Everybody gave us an odd path
You're supposed to talk like that. His little man bun thing. Cut it up. Yeah, I thought that was so cool.
They just never did it. She said like you didn't have to hair. Cut it.
It looks so cool. Spirit both sides. Spirit both.
Hey, before you put it in the sheet protector, sorry. I have one thing I want you to write on the bottom. I forgot to type on there. My apologies. It's just on the very bottom. There's a space. Write the following. I think this was in your notes last time, but this page is a good place to put this statement. You'll have to kind of write small. But I believe I told you last time, not positive when we got this far. Concave up, back up. Okay. A function is concave up. So write this down. A function is concave up. A function is concave up when the tangent slopes. So a function is concave up when the tangent slopes. Function is concave up when the tangent slopes of that function. Function is concave up when the tangent slopes of that function point by point. So like you're looking at a tangent slope followed by another tangent slope followed by another tangent slope. So function is concave up when the tangent slopes of that function point by point are increasing. That's the definition of the word concave up. And it's specifically why, like, so look at that chart I just gave you. this Danika's chart. Look right here. So a function is concave up when the tangent slopes of that function, well, the y values of f prime each represent the tangent slopes of f. So when the tangent slopes of f are increasing, that's what causes f to be concave up. That's all I've done. In fact, this whole sheet, all this is like Danika's chart in word form. So once you understand this, like Kenna made a good comment, she's like, I need to shrink this down to some card I can pack around with me or something. Honestly, once you understand how to read this, you don't need any of the rest. Like this alone will remind you of all the other words once you make sense of it. So, for example, I don't really have any of this memorized. Like when I type this, all I'm doing is looking at this, and I'm just reading the chart. So. But I put it into words just because over the years I have noticed that some people struggle a little bit initially to kind of make sense of it. You should also notice this. Hey, go. There's a lot of redundancy. So I'm going to show you one. Follow along on your chart and make sure that this idea makes sense to you. We won't do each of them. That would become really tedious. And maybe Haley are tired of that, so we won't do that. So, all right. Notice here it says, any function. Okay, crucial that you get this. Any function. That means it could be f, or f prime, or f double prime, or whatever. Just any function has an inflection point when that function changes concavity. That's the definition. Or, this is the one I just told you. When that's, well, I guess I didn't, sorry. So changing concavity. So, or when that function's derivative. So here's the key idea. I could be talking about f having an inflection point when f's derivative, which is f prime, changes from increase to decrease or vice versa. So just to give you another example of how to think of that, if you look down at this table, you'll see right here, f has an inflection point when f changes concavity. It's the same thing, just different words. Any function has an inflection point when that function changes concavity. Or when that function's derivative changes increase to decrease or vice versa. So the wording is very redundant, but just slightly different to impress upon you the meaning of the chart. Questions? Perfect. Okay, next thing. So now we understand that. Let me just do one other visual example here. So look at this. This is in your white note, the white packet I gave you last time we were looking at it. Just want to make sure you're clear on what this chart means. So again, I'm going to be referencing, you're fine. So I'm going to be referencing this verbally while we look at this. So you have this in front of you so you can correlate the two. Does that make sense? So for example, we just got done writing that any function, or say a function, is concave up if that function's tangent slopes, point by point, are increasing. Another good thing to remember is this. Concave up is this shape. And I didn't put the concave down definitions because it's just the opposite. Same thing, I don't have a relative min definition in this note because relative minimum is simply the opposite of relative maximum. So it saves some writing. Concave up is this shape or any part of it. Concave down is the opposite. So as I look here, now let's do a whole bunch of whole class of points. You can start adding them up for extra credit. As I look here at the blue function, I want you to simply raise your hand when you can tell me approximately at what x coordinate does the blue function change from concave up to concave down. Just raise your hand when you can see it. At approximately what x coordinate does the blue function change from concave up to concave down? So we did a whole series of whole class questions here. Concave up to concave down. Let's try Connor. 0.3 is really good. So it turns out, yeah, it's very good. It's probably about 0.25, so that's excellent. So he's looking right here. He's looking right there. How many saw it before he said it? Joe, point. Questions? Oh, please.
I was looking at the other one. I was at 3.
Because I was looking at the other spot.
Oh, gotcha. Oh, that counts for sure. Not a worry at all. I was just following it from here, Ethan. So concave up, concave down. You're fine. There we go. Awesome. Okay, now notice this. Watch me. If I look at the slopes of this function in blue, I see a negative tangent slope followed by another negative tangent slope, etc. So I'm looking at the tangent slopes point by point. Okay? Now notice, this is very negative, less negative, less negative, less negative. So if we come to a back. If I keep following, I note that here the tangent slope is exactly 0. I'm now negative, but now more negative, more negative, more negative. Okay? So, question for the whole room. If you follow the tangent slope, slope by slope, and this isn't a trick question, I want to make sure you know it. Raise your hand and tell me what's the x-coordinate for the tangent slopes of f, because the blue function is f. What is the x-coordinate where the tangent slopes of f change from increasing to decreasing? Like here the tangent slope is negative, now it's less negative, now less negative, less negative, now 0, now negative, now more negative, now more negative. So we're looking for the tangent slope changes from being an increasing point-by-point slopes to a decreasing point-by-point slopes. Okay, everybody. I'm confused about half the room on that one. Put some numbers on it, it helps. Okay, I don't know what this slope is, but it's pretty high, so we'll say it's about 200 negative. This one here is about 140. Oh, I'm looking at the wrong graph. Yeah, that's right. That's about 140 negative. This slope is about 130 negative or so. And then when you get to here, this slope's about negative 10. This slope's about negative 15. This slope's about negative 20. So the question is, following the slopes of the blue point by point, at what x-coordinate do the slopes change from being increasing slopes to being decreasing slopes? Show me your hands. Who can see it? Oh, please talk to me.
So, are you asking when it stops being negative and starts being positive?
No.
Okay.
Let's just say it together then. Look up, look up, look up. Here's the way you read it. If I go from negative, a slope of, so first of all, just raise your hand if you're comfortable with this. From here to here to here to here to here to here, the tangent slopes are becoming less negative. Raise your hand if you're comfortable with that, first of all. Is that, I know Kiss has a question, are you comfortable with that so far?
No, I think I know it.
Oh, good. Raise your hand so far. So who's comfortable with this? Negative, 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 but less negative. Everybody comfortable with that?
With the x being less negative?
Not the x.
Oh, the y.
Not the y
Oh,
either. The tangent slope. Tangent slope. Because
I got now.
you're good. We're focused on that statement you just wrote, Ethan, that a function is concave up when the tangent slopes of that function are increasing. So what's weird is this. These are negative values. But are those negative values increasing or decreasing? They're becoming less negative, but we call that increasing. That's what can be confusing. It's literally like a temperature scale. The temperature is going from negative 200 to negative 140, so the temperature is increasing. Please, Karen.
So, how come we don't just look at the orange one? Because it's easier to tell that it's increasing when
Oh, no, that's perfect. That's perfect. The reason I want you to see it here as well is because you're going to see problems in the future where they won't show you the orange.
Okay.
And so it just has to make sense, that's all. But you're perfect. You know, the orange dots indicate these slopes, right? So the y coordinates here are definitely increasing. Perfect. Anybody else? Good comments. And then look, so here f is concave up. Now f is concave down. Watch what the slopes do. They become negative, more negative, more negative. Like the analogy I gave to Kenna, the temperature is dropping, those slopes are decreasing as you go from slope to slope to slope. Does that make sense? That's what this statement that you wrote means. So the one you wrote at the bottom is what I just showed you. We'll have a follow-up question on that. Awesome. Okay. Danika's chart. Let's just apply it to this for a minute. So, okay, so here's how you read Danika's chart. Again, this is just Danika's chart in lots and lots of words, but I just use this. Okay, so if I'm taking a test, I just write this on my test, and I just keep using it over and over again. For example, you said that F switches concavity right here. When F changes concavity, F prime has to change from increase to decrease or vice versa. So look at it. Here's F prime. F prime is increasing. Right at the point when F changed concavity, F prime changed from increase to decrease. Question, Paris, please.
So, if sometimes, like, it's probably harder to tell sometimes where the concavity changes, so you would just look at where it's increasing and decreasing.
Perfect, perfect. That's really, really good. It is much harder to tell exactly where the concavity changes than it is to tell when F prime changes increase to decrease. Perfect. Please.
If they don't have the F prime, what's the?
Awesome. If all you see is F, and the question is, where does F change concavity, they don't expect you to find it perfectly. They'll only expect you to find it generally. So really, anywhere in here, they'd say that's good enough. Is that your question?
Yeah.
Yeah, they do want you to be able to visually look and say, hey, when are we changing from this type of a curve to this type? And remember, it doesn't have to be the whole curve, just any part of it. Like here we've got kind of the first part of the curve, and then it switches to this part of the downward curve. That's good enough. Is that your question?
Yes.
Perfect. Anything else? Okay. Another example, look here. When F is changing concavity, F double prime is changing from positive to negative. And sure enough, the y-coordinates here are all positive, and right at that spot where the concavity of F changes, the y-coordinates of F double prime become negative y-coordinates. Perfect. You got the idea. You okay? Let's move on. Now, in the white packet, just so you know, there are several examples. We won't do them together because they're honestly just a little too easy. They give you, they're just there for your reference. They give you a plot of a function, and you're supposed to plot the derivative function. It's literally as simple as saying, somebody can help me. Right here, somebody raise your hand and tell me the tangent slope here, is this tangent slope positive? Just say it out loud. Is it positive or negative? The tangent slope, positive or negative?
Positive.
Louder.
Positive.
Very good. So that means the y-coordinate on F prime has to have a positive value. So if I'm plotting F prime, I just draw a positive y-coordinate, like that. Now if I go to the next one,
Still positive.
yeah, more or less positive. So the next dot that you draw is less positive. The next one,
Positive but less.
positive but less. So the next dot I draw is positive but less. Slope right here, 0. So I put a dot with a y-coordinate of 0. Here, positive slope. So positive slope. This one more positive. This one. So the graph of F prime looks something like this. F. Then F prime, no, prime, you just do it again. So the white packet has, and then here's the answer, look. So here's F prime. And here's the numeric values they calculated with a computer. And I just gave you several examples if you need to look at them. Okay? Questions about what's in the white packet? Awesome. So next thing. Okay. let me pass out one more thing. Now tonight, the homework, first of all, remember this. I'm giving you 3 packets, not because the number of problems is much worse than like a previous homework assignment. It's just because there's so many graphs that it's hard for the copy machine to make them into one big packet. So the assignment tonight is the yellow, the blue, and the gold. We're going to spend the next 40 minutes though doing as many examples as possible from these packets to give you a really big head start. Look, eyes on me. Okay, it is a college level class, so you do have to have big assignments. I can't do anything about that. Because we have to be ready for May 15th. And I have to keep a certain pace. But really, first of all, it's a lot of graphs. So a lot of times it's like 1 page, 1 problem per page. Secondly, once you get the hang of it, a lot of them go quickly. Third thing, look at me. When I see you again on Tuesday, I don't necessarily again expect that you will have successfully completed all of the problems. I do expect that you have successfully attempted all of the problems. And then we have lots of time on Tuesday. Like we really can have a big long advisory period where you just ask and ask and ask to make sense of whatever problems caused you trouble. Does that make sense? So just, I get that it's, seems like a lot, but part of that's because we haven't had any for a couple of days. We just had to get the concepts down, now we can start applying them. So I'll pass this out, we're going to do a lot of examples. So you're welcome. As always, the answer to every single problem is in the back. So that's what I'm not sure that's your question. Not yourself. So for example, when we look at I'm looking at one function. They follow the curve. This white one smoke. No longer looking at the white. This is very negative. I'm going from slopes that are negative to
oh my gosh, he looked so good. Oh my He's always been everyone's psychic. Young people like gossip because we dress up in the house.
Not the yellow, not the yellow.
I love really hard. I made my coolest
Grab the yellow. So don't talk now that I'm talking. So, the first thing, don't let some of the problems in the yellow packet, you really have to read them slow and careful. I probably didn't give you one, so it isn't on. Sorry, thank you. Hey. Yep. Oh.
It's pretty. Oh, the other day.
There you go.
Sorry.
That's fine.
It's like, what the heck?
All right, here we go. Okay, you got to read super carefully. So look, follow the words, and if any part of it, okay, what did that mean? Just stop being stop. So, it says, which of the following graphs? This is problem number 1 in the yellow. Which of the bright yellow? There you go.
Number the golden rod.
Yeah.
Sorry.
Got to keep those colors straight. Which of the following graphs? Which of the following graphs A through D? So which of these could represent the slope at every point? Okay, listen, folks. Slope at every point of the function graph here. So what they're telling you is, here's some function. Now this could be f, it could be f prime, it could be f double prime. They don't say, it's just a function. But the slope at every point of this function is graphed below. So now you know for certain this is some function and this is that function's derivative. Are you having trouble with the question? Okay, turn in the packet to number, just so you can see the contrast. I believe it's number 5. No, that's not it. Sorry. Next one over. Number 7. Might start with 6. Yeah, number 7. You check the wording in 7, how it's different. Look. Which of the following graphs, A through D, could represent the function whose slope at every point is graphed here? So they switched it on you. You see the difference? So now they're showing you the derivative plot. This is the derivative of some function. This is, where the derivative came from. We need to say that again or differently. Okay.
Yeah.
The short way to say it, David, is this. Now remember, okay, so it says which of these graphs could represent the function? So that means, I don't know, f prime's the function. Whose slope at every point is graphed here. That means this function's slope is graphed here. So if this is the slope of this would have to be f double prime. Does that make sense? Yeah. The other way to look at it, David, would be to say, they're giving you, instead of that, they're giving you f is down here, f prime is up here.
How do you know that?
So it's from the wording. Which of the following graphs, A through D? A through D are the graphs down here, Connor. Which of the following graphs, A, B, C, or D, could represent a function whose slope at every point, okay, is graphed here? So these y coordinates are graphing the slopes of these graphs. That means this, it all depends on what you start with. We start and say this is f, then this is f prime. We start and say this is f prime, then this would be f double prime. It's all relative, it doesn't matter, but that's the idea. Please.
So in order to solve it, tell me if I can do something. Would we use Danica's chart and say, hey, it's positive, so we know that if it was negative prime, it would be increasing.
So here's what Kenna just said. Let me just write it down so they can all hear it, Kenna. You're doing really, really well. Just stay with me 1 second. So what Ken is saying is, okay, so I'm looking at a picture of f prime. And her first observation was perfect. She said, hey, all of these y coordinates, they all have positive values. So if the f prime graph has all positive y coordinates, you say that the f graph must be always increasing. So what are your options so far? A and C. Stop right there for a second. We're going to have a follow-up question on that. Let's go here.
How come f prime isn't also like at an angle because it's?
Oh, you'll see in a second. It's very good. Good question. Hey, look up. Are we good so far? Ethan, you had a hand up? You're okay. Never mind.
Yeah.
Okay. Somebody else. Kenneth, that's your question so far.
Yes.
Okay. Somebody else do this now. Kenna picked out this characteristic of f prime. She focused on when f prime was positive versus when f prime was negative. This is why the chart is so helpful. The only other thing to consider is this. Ethan.
So obviously it's not increasing or decreasing because it's a horizontal line, so that means it can't be C because C is a concave.
Perfect. Perfect. I'll just say it back to the room. And one thing here, everybody look up. I think I teased you about this. Don't say that word anymore because it has no meaning. Have I mentioned that?
Cancel?
Yeah, don't say
Oh,
cancel.
oh, yeah.
Don't say this either. The reason why is now that we've started to study a function's derivative, and a function's second derivative, if you start using the word it, you completely lose track of which of those three you're referring to. So just don't use it. On the AP test, if you do that, you'll lose points rapidly. Just talk about f prime, f double prime, or the function and its derivative. So what Ethan just said was this. Since this is a graph of f prime, we're assuming, and because this graph of f prime isn't increasing or decreasing, that tells you that the corresponding graph of f cannot be concave up or concave down. So it can't be this one. This is the only possibility. Questions to that? You know, answering Paris's question, notice this, Paris. You can actually calculate it. The rise over the run, Paris, what's the rise over the run for this section? 1 over 1. It's going over 1 while it's going up 1. Does that make sense?
Yeah,
So this has a slope of what, Paris?
1.
1. And does that slope ever change? Is the slope always the same? Always the same. That means at every single point, the slope is 1. That means every single y coordinate has a value that is 1.
Okay.
Does that help?
Yeah.
Good. What else? Cool. Let's go to number 5. That's another example. Okay, Danika's chart again, so I just draw it. I personally find it difficult to explain any of these problems without having Danika's chart written down in front of me. Okay, make sure you make sense of the idea, this is what David was asking about, that this is the opposite. Now they're saying, which of the following graphs, A through D, so which of these could represent the slope at every point? So now it's like they're saying the one up top is f, and we're trying to identify the matching f prime. Here's where I would always start. First identify, let's see, the y coordinates of f prime, they represent the slopes of f. The easiest slope of f to always find is where f has a slope that is equal to 0. So we'll pay the whole room for this one. Raise your hand if you can tell me what's the x coordinate on f where the tangent slope of f will be 0. Hands up. And there's 2 of them. What are the 2 x coordinates on f where the tangent slope of f will equal 0? Let's go, Chelsea.
Pi over 2, 3 pi over 2.
Chelsea looks right here and she says, okay, that tangent slope is 0. She looks right here and says, okay, that tangent slope is also 0. That means that the y coordinates of those spots on the f prime graph have to have y values that are 0. That's the correspondence between f and f prime. Okay, how many knew that before she said it? Point. We have a question. This class is really good at questions. So just, everybody? Like you really are. Like, and honestly, hey, My ideal is every single class period, simply I say a little bit, you ask a bunch of questions. Like that's the best class, so don't ever stop. You good? Please.
Sorry, is it just 0 because the slope's not going anywhere?
Right. So no, it's perfect. So one way we think of slope, Eric, is rise over run, and this has no rise, so the slope is 0. Perfect. For the else. Awesome. So hands up. We'll pay the whole room. So which are possibilities so far? Like we're down to just 2 of them. So hands up if you can see it. Which 2 are possible? Knowing that the tangent slope at these 2 spots has to be 0, right? So Ryan says B and D were, because he goes to x equal pi over 2, x equal 3 pi over 2, and sure enough, those y coordinates are 0, whereas over here, the y coordinates at those 2 x coordinates are not 0. We need me to say it again or different?
Yeah, can you just say it in a different way?
Yeah, usually what helps the most is that you and I just talk for a second. I ask you some questions, okay? So are you comfortable that on F, at these 2 x coordinates, we have slopes that are equal to 0?
Yeah.
Perfect. So what that means is right away you could write this, Kesta. You could say F prime, the slope of F at pi over 2, that would have to equal 0.
Okay.
Does that make sense? And then F prime of 3 pi over 2 would also have to equal 0. So I go looking down here to see where that happens. Okay, at this x coordinate, is the y coordinate equal to 0?
No.
How about this one?
No.
So that's not it. How about this one?
Okay, I was just like confused in the sense of how that one's 0, and then for C, it's kind of like the same position, and it's not 0.
The difference is,
Yeah.
this is kind of what I was talking to Brinley about. Up here, I'm paying attention to the slope, not the y coordinate.
Okay.
Because I know that the slope of the f graph is represented on the f prime graph as a y coordinate.
Okay.
So yes,
That makes
this
sense.
does have a tangent slope of 0, but that's not what I'm looking at.
You're looking for
Y
the
coordinate.
Okay, that makes
Yep.
more sense.
Cool. David, please.
I think this is kind of what Ken talked about earlier, just that like, why are we trying to find 0? Like, why?
What we're trying to do is figure out, this is f. Without actually having to draw f prime point by point, we're trying to just find a match. So the easiest thing to match up, first of all, is wherever f has a tangent slope that is equal to 0, f prime will have a y coordinate that is 0. I would actually write that down if you're having trouble with those. Wherever f has a tangent slope that is equal to 0, f prime will have a y coordinate that is 0. That's what I was saying to Kesta. It's that correspondence between looking at tangent slope here and y coordinate here. Please. So wherever f has a tangent slope that is 0, f prime will have a y coordinate that is equal to 0. And please remember this, it doesn't apply just to f and f prime. It's any function that has a tangent slope of 0 at some spots going to have its derivative have a y coordinate at that same spot. So, does that help a little bit? Okay, we'll keep going, please.
So technically, you can count, well, in these questions, you can find how many times the tangent is 0, and then look on the next graph and find how many times it's 0.
Absolutely. Oh yeah, for sure. Like what Ken just said, you look up here and you say, hey, there's 2 x coordinates where the tangent slope is equal to 0. That means that those exact x coordinates, like you got to line them up, but those exact x coordinates, I've got to find y coordinates of 0. Yep.
Is the inflection point like the tip of the concavity, or is it like the halfway between the
So any function has an inflection point when that function changes concavity. So that occurs right there.
Okay.
Yeah, good question.
And
Go ahead,
sorry.
please.
And then like the tip of the concavity, is that all the slope always going to be 0?
Not necessarily. So I would memorize that.
Okay.
That just is happening here.
So how can you tell it's 0?
that it's flat. So basically you just follow the curve and say this tangent looks kind of like that, this one looks like that, getting flatter. At the very top it's flat. Okay. So part of what I said, I may have misled you. Yeah, anytime you have a bump of any sort like this, I don't want you to tie it to concavity, to be honest.
Oh, okay.
But like a bump like that, or a big wide bump, or whatever. Yeah, the top of the bump, bottom of the bump, it's always.
Okay.
I think that's what you meant.
Yeah.
What else? So we're down to these two. So now I need someone to volunteer and tell me, okay, we paid attention to when the slope was 0. Now someone just needs to pay attention to either this one and this one, or this one and this one. So when Nate talks to me.
Well, I just followed it and it was increasing.
So what Nate said is, look, he said right here, F is increasing because the y coordinates of F are going up. When the y coordinates of F go up, the y coordinates of F prime have to be positive y values. So he looks over here and says, oh, that's a big problem. Here when F is going up, these y coordinates are not positive. These y coordinates are, this is the correct answer. You're done. Just stop. And the key thing to focus on, Kesta and everyone else, is notice how specific I am being with regard to, am I looking at, am I looking at tangent slope, or am I looking at y coordinate? The other thing to pay attention to is the x coordinates always match up with the f versus f prime. So I'm looking right here in this region, and I see that the y coordinates of f go up.
Yeah.
So look at the chart. The y coordinates of f are increasing.
Yeah.
Therefore, the y coordinates of f prime must be positive values. Is this a positive y coordinate?
No.
Can't be the right answer.
Okay.
That makes sense? Perfect. Is this one a positive y coordinate?
Yeah.
Awesome. I just had to say that somehow I felt stuck without saying it. Is everybody good? Next one. Go forward now. Let's go to number 11. Go to 11. Okay, the AP test never does this. The AP test never gives you a multiple choice question and then have several of them be correct. The AP test never does that. If they do that on the AP test, the format is they'll give you like Roman numeral 1, 2, and 3. You've seen this before.
Yeah.
Then below it will say, it's 8, is it 1, is it 1 and 2? So this is a little different. What I want you to do as a class is to everybody use Danika's chart to identify which of these are true. And I will give you the hint that several of them are true. Okay, there's some that are false, but several of them are true. You're looking at F. Use Danika's chart to identify which of these statements are true statements. I'll walk around the room. If there's a question that comes to mind as I walk by, you stop me. Feel free to talk to each other. Oh, great comment. So what?
Why do we need the chart if we're only looking at?
Yeah, I get you. They just ask questions like that sometimes. So you're right. To answer some of the questions, you don't need the chart at all. No, that's perfect. But to answer any question that relates a function to its derivative, then I use the chart.
X.
It does. Which one? No, the question says the graph of f is shown here. And which of are considered for this function?
Is it the whole I think it is. I think it's and then F double prime is not negative because it's not negative because it's not concave down, it's not increasing down, it's not so it's here's a
I don't know what it
So after prime is the top. So the slope is where? Not anything. I don't know Z. Okay, it ends at why?
This sounds familiar.
Oh no, I didn't relate it to this.
Where the chart really. So this is perfect. What they want you to notice is that change in slope right here.
It's worded the same way 7 is, so I was to use the same. Right.
The slope is going over about the
It's giving you the slope.
So the slope is about 1/2. So the slope at x equals 0 is about 1/2.
So I was thinking for D, the slope would have to be like more and more. So like one it could be 1, and then
The
the
white
2
coordinates down here is the
and then at
slope.
like 5 would be like 40.
So that can't work. But this one, if I draw a tangent slope here, you rise over.
You know what I'm saying? So then I thought that
Drawing's
the
not
slope
perfect.
wouldn't be right
Tell that's
because
not
it
one,
was like
because the rise is
the exact same. Does that make sense?
That's what her question is. That's her question.
I tried to find this. It's how
So this one's complicated. This is our starting because it's concave up. Yeah, that's what I thought it would be because I'm like, okay, it's increasing, so this is positive the whole time, and it's slope to half. It should be like
Okay, well, yeah. I got it. Because it's the wide coordinate. So, I have never. I don't think you find it.
I never hear from the cars.
If it's F prime, that's just the wide coordinate.
So then that morning.
Let's move on from it tonight. So okay. Slope is decreasing, so that means it's being concave down. It's positive and concave down.
Because it's always what is second derivative?
No, is this
It's always decreasing.
I think it looks weird if just have that same.
no concave down?
F prime is always decreasing.
I'm trying to think and decrease. So look, increase, decrease. I don't think it matters.
Because you're going
It usually might have. It usually does.
So I feel like that was a whole thing. I get everything, but I'm not sure like what's slope. I don't feel like I'm really about to Would you ever get something different? The whole line's decreasing, which means. No, no.
Oh, yeah, if you get white
But there's no, Danica's chart doesn't tell us the difference between if it's.
Yeah, how do you tell the difference between how do you tell if it's like a sharp?
I don't know if that's like.
Or did
So we
you
can get up in like 5 minutes. I'm gonna ask. This is talked up a few times. I feel like it's a similar problem. We don't know if this
Hey, look at 3, but 1 second. Look at 12%. Look, once you finish, jump on to the questions. That's really smart. Hey, look at 12 for a second. Look at 12. I'll explain it, and if I didn't answer your question, Jake, just ask me again. Okay, it says, they're giving you F. What? It's extremely important that you pay attention to what they're giving you. And then you identify what are they asking about. So they're giving you F, but they're asking about the second derivative, F double prime. So Danika's chart again. Again, I emphasize again, as you're working on these 3 packets, don't ever get stuck too long on one problem. They're not in order of difficulty, they're just all over the place. Keep moving so when you come back on Tuesday, you can honestly say you tried your best to get through each problem. You know which ones to ask about. Okay, look. If I'm looking at F, and I'm trying to answer questions about F double prime, I'm focused completely here and here. And I notice that this section of F here, concave down. So that means the y coordinates on F prime on that interval would have to all be negative. So at this point, this y coordinate has to have a negative value. Here, F is concave up, so at C it has to have a positive value. So here where F is not concave up or concave down, it can't be positive or negative. And you're asking that in correlation to something else, though. Okay, she's no worries, you're good now. Okay, look at me, please. Hey, no, please, question. You're okay. So you're comfortable that here, F is concave down, so the value of F prime at point A would have to be negative. Here, F is concave up, so the y coordinate of F prime at x equals C would have to be positive. The thing, here's what's happening, look. F is changing from concave down to concave up. This is an inflection point. And if F isn't concave up, the value of F prime can't be positive. If F isn't concave down, the value of F prime can't be negative. Only one possibility remains, 0, or undefined. So that's how I know that at C, F double prime must be 0. It's more from the fact that you're changing from this type of a curve, to like this part of the curve, to this part of the other curve. And an inflection point, that always happens.
How do you do acceleration?
Yes, yes. Hey, go. We got like 3 minutes. Hey, go to the gold real quick. Sorry, Jake, one second. Go to the gold real quick. Just want to do a quick example on the gold. Yeah, look at gold. Sorry, look at gold number 2. Look at gold number 2. Okay, they're showing you f of x. Gold number 2. They're showing you f of x. they then ask, on which of the following intervals will the first derivative of f be positive and the second derivative be negative? So I do it little by little. I first come to Danika's chart and say, okay, initially, f is increasing. From A clear to C, f is increasing. Everyone see that? So the y-coordinates of f go up. If the y-coordinates of f are going up, the y-coordinates of f prime have to have positive values. That's what they wanted to know. When do the y-coordinates of f prime have positive values? So that's from A to C. We have a follow-up question on that. Okay? Let's see. When is the second derivative negative? So come over here and say, oh, when the second derivative is negative, meaning the second derivative has negative y-coordinates, the original function must be concave down. That's true from B all the way to D. So the question is asking, when are both true? It's the overlap. So B to C is where both of these things are true. That's how you logically think through that problem. Questions? Again, as you do the homework, please do not take too long on any problem. Get used to the idea that on the AP test you don't get stuck. Keep moving. Do your best to logically reason it out. You don't work backwards from the answer. You look at the answer and go, okay, my logic seems sound. I'm getting the right answer. If the answer doesn't match, think about it again for another minute, and if I'm not sure, just mark it and move on. Good work. Homework is the 3 packets. Welcome to BYU. Okay, let me back up and do it again.
AC is increasing, BD is concave down.
We just gotta go slower.
Decreasing.
Yeah, I just want you to
How did you get the answer?
think about this. They want to know when the first derivative is positive. Look over here. I want to know when we have prime that's positive value. I'm not looking at that prime. I'm looking at that. Oh, that means f prime y coordinates wrong. So where do we have prime y coordinates wrong? Right away, I'm only looking at these. Then it says second derivative is negative.
Calling students up to the main office. Kennedy Call, Nathan Hayron, Tyler Hill, Blake Whiting,